Okay, welcome to the second half of our warm-up, which is part one of our lecture series from Wednesday, April 12th. We have set everything up so that we can begin to do our stoichiometry. So now it is time for us to actually do our stoichiometric analysis, or mole ratios, mole counting. And that includes now the concept of looking for a limiting reactant. So let's do our limiting reactant analysis, because we know that once the limiting reactant is completely consumed, by definition, the reaction has to stop, and the amount of product is limited. In other words, the limiting reactant determines the theoretical yield of product, meaning how much product the reaction could be made if these mole quantities are reacted in their stoichiometric proportion, meaning according to whatever the mole ratios are in the net ionic equation. So it's just a little bit of review of definition of a limiting reactant. So remember, anytime we do a limiting reactant analysis, we are trying to answer the question, if each mole quantity of our reactants are completely consumed, which reactants consumption results in the limited or smaller yield or quantity of product. In other words, which reactant, when used up, limited my product. So we have to do a comparison. So let's start with our mole quantities of both reactants. And then we're also going to need the net ionic equation, which relates for us how these reactants react in proportion. So I've got 0.0133 carrying my 374. Moles of zinc available to react. And then I had 0.0450 moles of HCl to react. And let's go back up to what the problem is asking. Remember, I did change this a little bit. We want to know about the resulting concentration of zinc ion in solution. So the product of interest, looking at our net ionic equation, is the zinc. So this is the product of interest, meaning this is what we are going to be looking at in our limiting reactant analysis, meaning this is the amount of product we're trying to figure out becomes limited. All right, so this is where we have to use the mole ratios as given to us by our balanced chemical equation. So we're going to use our net ionic equation, given up here, highlighted in pink. So looking at what this says, for every 1 mole of zinc solid reacted, which is what I want to cancel, so that goes on the denominator, 1 mole of zinc reacted, I generate, according to the coefficient in front of my zinc ion, 1 mole of zinc ion. So these things react in a 1-to-1 ratio, meaning that the mole quantity of zinc ion that could be made if all of my zinc metal is dissolved is going to be the same as the amount of zinc metal that was dissolved, which, makes sense, right? All of the zinc ion in solution had to come from all of my zinc metal. So 0, 1, 3, 3, 3, 7, 4 moles of zinc ion. All right, let's see here. Let's do the same kind of analysis for hydrochloric acid. Now, we have to be a little bit careful here because we are doing our limiting reactant analysis based on our net ionic equation. So notice this is HCl. So before I can do any kind of stoichiometry that involves the mole ratio between zinc and my acid, I need to not look at molecular hydrochloric acid, but rather the mole quantity of H+. So this is where we look at our subscripts in our chemical formula of hydrochloric acid. This is 1:1, acid to chloride. So that makes our life kind of easy because that means that for every 1 mole of HCl dissolved, I put in 1 mole of H+ ion. And now that I am looking at the actual reactant that is used according to my net ionic equation, I can use my mole ratio, which tells me the proportion in which hydrogen ion and zinc ion are reacted and made. So according to my balanced net ionic equation, there are 2 moles of hydrogen ion reacted for every 1 mole of zinc ion produced. So I am doing this is, mathematically this is saying multiply by 1 and then divide by 2, but I'm doing this way to ensure that all of my units cancel, right? Moles HCl, moles HCl, moles H+, moles H+. This leaves me in moles of zinc. Same deal here, moles of zinc solid leaves me in moles of zinc ion. So there's a reason why I'm writing it out kind of in this full manner so that visually to you guys, you can see something that makes sense. Like I'm not just doing math with units that come out of nowhere. Okay, so 0.0450 moles divided by 2 gives me 0.0225 moles of zinc 2+ that's made. And going back up to the kind of question we're trying to answer from our limiting reactant calculation, if each mole quantity of reactant is consumed, which of those reactants results in the smaller yield of product? So I've got the zinc that when completely consumed gives me 0.0133 moles of zinc ion. And then I've got my hydrochloric acid, which when fully consumed gives me 0.0225 moles of zinc ion. So since this is my limited mole quantity, this is my theoretical yield, meaning that the solid zinc, this is my limiting reactant. Okay, let's go back up to what this question is asking. What is the concentration of zinc ion in solution? So as always, when we're talking about an aqueous reaction, it's a good idea to kind of put yourself in the beaker, thinking about what ions are present, in what proportion, yada, yada, yada. So let's look at reaction from the beaker's perspective. All right, so I had some solid zinc metal that was dissolved in 15 milliliters of hydrochloric acid. And this is my pre-reaction condition, where the mass of zinc was my 0.872. All right. What's happening afterward? So we said that the limiting reactant, according to our stoichiometry here, is the solid zinc itself. So I would not expect to see any solid zinc in my reaction flask at all once the reaction has concluded. So here, post-reaction, we see that all of our solid zinc is dissolved, and we know this because zinc ran out first because it is our limiting reactant. Meaning that I've got some hydrogen gas that's being formed, and then I also now have zinc ion in solution. And remember, my net ionic equation says that my zinc metal and my zinc ion exist in a 1-to-1. The only thing that I haven't included in my original solution is my stoichiometric proportion of H pluses, and also don't forget those chloride ions. And now I have here, post-reaction, I've definitely got those zinc and chloride ions. However, notice that is not all that's going to be in this beaker, because I had used up all my zinc metal to make all my zinc ion. So this was my limiting reactant. I consumed all of my zinc. And since I did not consume all of my HCl, that means I have some excess H ion left over. All right, let's finish this problem. Concentration of zinc ion. So remember, concentration, molarity is moles. So for this is going to be our moles of our zinc ion that are in solution over the liters of the solution containing our zinc. We are going to assume that this reaction did not change our reaction volume by much, so we have 15 milliliters of volume here. And since we know our moles of zinc from our limiting reactant analysis, then all it is a question of using our definition of molarity to determine the proportion of moles of zinc ion and the volume of zinc ion made as a result of this reaction. So my moles of zinc, let's see here, 0.033 carrying my 374 moles of zinc. And then I'm going to divide that by my volume of solution, which must be in liters. So I'm going to take my 15 milliliters and divide that by 1,000, or move my decimal over to the left 3 places. So I'm doing this conversion from milliliters to liters in my head. That gives me 0.0150 liters of our reaction solution. So let's see what we get when we do that. So again, carrying all of my digits in my calculator. So that's all my 3's. And then dividing by my dividing by my, product beaker volume. This gives me 0.88916. So that's every digit that my calculator gave me. Molar. And the sig fig analysis here, this had 1, 2, 3 sig figs. This also had 1, 2, 3 sig figs. So I need 1, 2, 3 sig figs in my overall results. So I can report the concentration of zinc ion in solution once the reaction has stopped as being 0.889 molar. And this is my answer to this question. All right, so in general, anytime you're doing any kind of stoichiometry, we now have to consider the limiting reactant. So you're always going to set yourself up with your balanced chemical equation to get your mole ratios, ideally your net ionic equation. Then you are going to use the lab quantities that are given to calculate your pre-reaction mole amounts that are going to react with one another. And then you're going to use those reaction amounts and what you know about their mole ratios to give you an idea of what your theoretical yield or actual amount of product is that is made based on what your limiting reactant is. And then from there, once you have moles, you could do things like put that in grams, put it into molarity, yada, yada, yada. So a lot going on in stoichiometry, but as long as you kind of follow that process of getting your balanced chemical equation, your mole quantities, and then doing a limiting reactant analysis, you should be fine. So coming up in our next video, we are going to look at some more practice problems, specifically looking at titration stoichiometry. So we're going to do an example of titration and neutralization reactions, which is going to be very similar to what we've seen in our titration lab. I'm also going to add an extra bit onto this. I'm also going to introduce excess reagents here, so I'll probably add in a little bit about pH, and you'll see what I mean in this next video. And then from there, we will again just come back and discuss this idea of a theoretical yield, which we know by now is the amount of product that is made as a result of the limiting reactant completely reacting. We'll compare that to what's known as an experimental yield, and then calculate lastly a percent yield, and that will be all for today. So coming up next, part 2, titration stoichiometry practice in our third video.